So we've built out the 3-bus machine, and we've introduced the idea of control points and a micro instruction, which is a collection of control points. And we're going to just trace out the execution of an instruction on this machine so we can really get a handle on what all this looks like in a concrete example. So with this instruction, store into the address M the value that's in register 0. First thing we have to do is fetch, because it's always the first thing we have to do, because until we fetch the instruction, we don't know what we're doing. So fetch, what we have to do is put the address of the next instruction into the memory address register, get the data that is the next instruction from the memory buffer register into the IR. So it's a 4-step process. Step 1 is we're going to copy the program counter to the memory address register. Then we're going to increment the program counter. Then we're going to do a memory read, and then we're going to copy from MBR, memory buffer register, into the instruction register. After those 4 things happen, we will have our instruction. So what does that look like? Step 1, program counter copied into memory address register. We enable the program counter onto the bus. We tell the ALU to pass that through, and then we clock it into the memory address register. Those 3 things: enable the program counter onto bus B, clock the memory address register, and tell the ALU bus A gets bus B. And again, we can put them in any order because it all happens at once. Now, the program counter value has been copied to the memory address register, and memory does its thing. But before memory does its thing, we're going to increment the program counter. These could happen at the same time, but we'll get there. So we're going to increment the program counter. We enable the program counter onto bus B, which is the same as we did before, right? So that same value is at the ALU. We're going to tell the ALU to add 1, and then we're going to clock it back into the program counter. No problems. That's the second thing we have to do, so that the program counter is ready for the next instruction. Then we're going to tell the memory to do its thing. We're going to read, which is the memory address register, addresses the memory, and the result gets presented at the output into the memory buffer register. And then we're going to tell the memory buffer register to grab whatever's there, right? We're going to clock the memory buffer register. It's a little bit of confusion here because the memory buffer register can take information from the memory or from bus A. So we might need a control point there to tell it where to get its information from. But for now, this will work fine. And that is the memory access, which actually loads the instruction. And then finally, we take the memory buffer register and put it, again, pass through the ALU into the instruction register. So those are the 4 steps that we need to do to get the instruction into the machine so we know what we're doing. Those 4 steps happen at the beginning of every instruction. And we call that the fetch phase, and then we will have the execute phase after that. Right? So there are these 4 micro instructions, and this is what we mean by micro instruction, right? The micro instruction is move the MBR into the IR. That's not really an instruction, right? An instruction is load information from memory, add 2 numbers together. A micro instruction dictates what the architecture should do to implement the instruction, which is what the math should do, right? The conceptual processing that we're trying to get accomplished by putting these instructions in order and doing things. What the hardware should do to make that happen is the micro instruction. So there are 4 micro instructions, and again, we could probably optimize this a bit, that allows us to get the instruction into the instruction register. And again, it's got to be common. Now, let's look at what happens for this particular instruction, store into address M the value that's in R0. Okay? What we're going to do is we're going to take the value that's in R0 and we're going to put it to the memory buffer register, because that's the only way we can get information into memory. So that is enabling register 0, that is telling ALU to pass through bus B, and then is telling memory buffer register to clock. Now there's data at the memory, but we don't have the address yet. So next thing we have to do is move the address from the instruction register into the memory address register. Again, enable the instruction register to bus B, clock the memory address register, and tell the ALU to pass through. Now there's a little bit of complexity here because the instruction register contains the opcode as well as the memory address. And we just want the memory address. So we might have to do some little finagling there to make that happen, but these are minor details. So the memory address from the instruction register into the memory address register. Then we just tell the memory to do its thing, right? We tell the memory to write. The data has been set up. The memory buffer register has the value. The memory address register has the address, and the thing happens. And that's the end of the instruction. So the actual microcode to complete the instruction is only 3 cycles, whereas the microcode to get the instruction into the machine is 4 cycles in this case. So a few things to keep in mind here. There is some duplication, and that's sort of the advantage of doing this in a microcode mechanism, is because that microcode, we might be able to do things more than once, right? If we just tell the memory to do the thing, it's the same whether we're loading an instruction or loading data, right? If we tell pass through to bus B, it's the same whether we're doing that for the program counter increment or for something else, right? And so we can reuse and optimize and really make efficient this microcode. The other thing is that instructions might take different amounts of time, right? This is another opportunity to optimize, and it stands in direct contrast to the pipelining conversation that we're having in that different set of videos. In pipelining, we want to make everything look exactly the same. But in this initial design for microcode, we can make things look different. So some things can be faster, some things can be slower, depending on how long the execute cycle takes. And when we actually build out and look at how sort of, floating point operations execute, or some of those other functional units in our pipelined superscalar machine later on, some of those units have their own pipelines and can optimize faster or slower depending on what they're being asked to do. So what can we do to improve this? This works okay, but what can we do to improve this, right? We recognize, for example, that when we increment the program counter and tell the memory to run in the instruction in the fetch phase, those two things, there's no overlap in that hardware. So both of those things could happen at the same time, right? So we can reuse components when they're not in use. We can recognize that there are some components used and some not, and optimize that way. So we'll have a look at that in a second, but let's do one more instruction just so we really get a feel for it. Here we're going to add 2 instructions together, or add 2 registers together. And the fetch is the same because it has to be the same, right? And then the last thing we do is we just take the 2 register values, present them to the ALU by enabling register 0 onto bus B and enabling register 1 onto bus C. ALU does its thing, we tell it to add, and then the result is clocked into register 1, and then we're done. A single clock cycle does all of the actual meat of the instruction, whereas it took 4 clock cycles to get us that, to get the instruction in place so that we can actually do the thing. Here's load R0M, right? This takes the data that's in memory at memory location M and brings it into R0. Looks very similar to the store instruction, right? IR gets MAR in the execute phase. Memory at MAR gets MBR. But then instead of putting the data into the MBR from register 0, we take the data from register 0 and put it into, other way around. Instead of taking the data from register 0 and putting it into the MBR, we take the data from MBR and put it into register 0. So we can reuse most of those steps, but we have to make it different at the end of that step. Now we recognize some things that we can do that make it a little bit faster, right? We recognize that the memory address register getting the program counter and the program counter getting incremented can happen at the same time. And we recognize that if we skip the memory buffer register, which again, maybe we don't want to, maybe we do, but if we skip the memory buffer register, we can make those 2 things happen at the same time and really optimize our development. So that's the 3-bus machine, which is sort of the maximal version of this, right? Have 2 buses, 1 for each input of the ALU, and then a bus for the output of the ALU, so that the ALU can serve its role as the heart of the machine. In the next video, we'll look at a few other architectures that might have different implementations.